Okay, so as most of you know, Newton was a pretty smart guy, and he has this method that he and actually, I don't know, I'm probably not going to say his name correctly, but I believe it's Raphson, both worked on this thing. So it's often called the Newton-Raphson method. It's the same thing. But anyways, you'll find it in your textbook as Newton's method. And I'm going to show you what Newton's method actually does, so you get an idea where it comes from. And then we'll talk about the details. So this was Newton's idea when he saw a function, right? So he sees a graph like this, and he wants to find the zeros, meaning he wants to find where the solutions are, like this one, say we're right where the mouse is pointing to. You guys have been doing that for a lot of your high school careers, right? Solving equations. But what when the equations are so difficult that it's like there is no simple process of factoring or moving things around. So Newton's method is like more general purpose, and I'll show you the way it works. So let's say that Newton's trying to figure out this solution, or a solution, there's a couple of them on the screen, to this equation here, right? And we know that the graphing calculator would find it for us in those spots. So maybe he says, I'm going to start at 2. Okay, so Newton says, I'm going to start at 2. And then what Newton's going to do is he's going to then say, where's the tangent line on that curve? Okay, so let's take a look at the first step. So there's the tangent line in blue. The tangent line then jumps over to where it hits the x-axis. That's his first approximation to the answer. So what you can see is he started over here at 2. That's how far away he was from the answer. Now look at how close he is between where that red dot is and one of the solutions. So then he's going to say, okay, let's go back up, find the next tangent line. So find the next tangent line. Where do we land? Okay, so it jumps back over quite a ways. And if we keep repeating this process, then it keeps getting oh, well now it's so close that you can't even see the difference as I move the screen along. It's found an approximation here, 1.364412, and going. So what you got to remember is he didn't have a TI-83 like you did, right? He had to figure out how to do this using simple addition, multiplication, subtraction. So he could take the derivative of this function, and he could do this all by hand, and he could actually solve some of these things. So let's just try another spot here. Maybe I'll zoom in a bit more so we can get a little bit better of a picture. So let's say we're going to look for the one solution that's shown. Maybe it's our initial guess is something like 2.3. Okay. So again, first of all, find the tangent line. That gives me a new approximation. Tangent line gives me the new one. And you see it's zeroing in, and now it's basically found it. So it keeps going that way. And let's see here. If we were to try something kind of silly, if we put in 2 as our approximation, you notice it didn't find the answer. So the only thing that you got to remember when you work with Newton's method is it may not find the particular spot you're looking for. It may find an answer that's different altogether. And there are ways to fool Newton's method that won't work at all. But anyways, I think, I'm not the number theoreticist, I guess, that some of you will encounter in university, but I believe Newton's method doubles the number of digits after each iteration. So like if you have 2 correct digits, the next time you do it, you'll have 4, then you'll have 8, then you'll have 16. I'm pretty sure that was the way it works. So it's pretty powerful as far as finding solutions goes. So that process of finding the tangent line and then lining up where the x-intercept is to get your next one, this is what it looks like right here. Okay, this is Newton's method. You start with an initial value, and you take away the function divided by its derivative. Okay, so all I've done here is shortcutted how Newton's method actually works. You could derive the whole thing based on that picture of tangent line to x-intercept, next tangent line to x-intercept, and keep going. Now, we're going to try 3 iterations to find a solution to this. So, again, you got to appreciate that they didn't have calculators when they first used Newton's method, but something like square root of 2. How could you figure out a good way to calculate the square root of 2? Well, if you think about the answer here, what's one of the solutions we should expect to find? Yeah. Sorry? one of the solutions to x squared minus 2 equals 0? Yeah, we'll get a couple of them, right? We'll get root 2 and we'll get negative root 2. Okay, so both of them would give us solutions, but what if we actually want to know what is the number root 2? How do we find it? So we can actually do it with, I mean, we'll use a calculator, but we could actually do this with pen and paper. So let's say, give me a guess, where do you think, we'll start as 1 being our initial guess. Okay, so this is, our first guess is 1. And what's the value of the function? So we put it in, 1 squared minus 2 is negative 1. We need to know the derivative, so the derivative is 2x. So the derivative at 1 is going to be 2. So this fraction, the function divided by its derivative is negative 1/2. So xn, take away this guy, is 1/2. Sorry, 1.5. 1 minus negative 1/2 is 1.5. So that then tells me what the next guess I'm going to use is 1.5. Okay, and then we're going to go through this table again. So this time, I mean, we have this luxury, so we might as well use it. If I put in 1.5, I'm going to get the value 0.25 for the function. I'm going to get 3 for its derivative. And 0.25 divided by 3 gives me 0.833, sorry, 0.833. And then when I subtract those two, I'm going to be subtracting my initial guess, take away that fraction. So it'll be 1.5, take away that value there, and it gives me 1.4166 going on and on and on. Okay, so that's now my next guess, the last one that we'll do by hand here. And we can keep as many decimal places as we felt was appropriate. So when I plug that in, I'll square it and take 2 away. Now I get 0.00694. Man, it's a good thing we didn't have to do this by hand. The derivative is going to be 1.41 times 2. So I end up with 2.83 going and going and going. And now I take the function divided by its derivative, 0.0069 divided by 2.8 and 33333. So I end up this time with 0.00245, and there'd be a 1 if we rounded. So now when I take that onto my original, I end up with about 1.41421, and let's round it there at 6. Okay, so I've done 3 iterations of Newton's method on this, and now I'm going to actually look in the calculator and find out what is the square root of 2. So square root of 2 is actually 1.412135 on and on. But if you look, I only did 3 rounds, and so far I have 1, 2, 3, 4, 5, 6 correct digits. So again, if you didn't have your calculator, how on earth did they do this kind of stuff before? Well, Newton's method was one handy way to find constants. Okay, but it's not just for finding constants. It's obviously still used today to solve equations, and that's what our primary goal is going to be. So, so I'm going to show you how to shortcut this, and this is why students seem to like Newton's method so much, is if you have your TI-83 with you, sorry I don't know how to tell you how to do this without a TI-83, but with your TI-83 I can show you a fast way of doing this. And basically I'll walk you through it, and then I'll show you on the screen, but for now you just have to follow along with me. The first thing we're going to do is we have to calculate the function and its derivative. So with Newton's method, you got to know how to take the derivative. So what I want you to do is I want you to then try and write this in as y1 and write this in as y2 on your y equals screen. So I'll just give you a minute to write those into your TI-83. Okay, and once you've put them both in, you want to get back to your calculation screen. So it's a blank screen with a cursor flashing like this. Okay, I'll give you another minute in case you're still entering it in. But you should have y1 and y2 filled in as the function and the derivative. Go back to your calculation screen. Okay, so now what I want you to do is we're going to enter in those functions. So we're going to get an initial guess. So let me take a look here. We'll figure out what initial guess might be good. So let's get a graph to help us out. Right, the graph's not going to be very exact at all, but it can help give us a good guess. So y equals e to the x plus x. There's the graph. So what do you think? You don't have to be super accurate. What do you think would be a smart initial guess here?
0.
So if we picked 0, this would be the initial guess here for that root right there. So sure, why not? Let's try it at 0. I mean, it would probably be, it's not going to matter because the calculator is going to do the work for us, but it'd probably be a little faster if we chose something more like, negative a half. But anyways, for now, let's go with 0. That's fine. So let's say my initial guess is going to be 0. So here's what we're going to enter in the calculator then. We're going to go 0 minus y1, and you have to put brackets in like this. So how do you get to these? If you remember how to go to y variables, you hit the variables button on your screen, and one of the choices says y variables. So that's what you want to enter into your TI-83, so it does all Newton's method for you. And it gets faster, so I'll just give you a minute to enter that into your calculator screen. Okay, so what I ended up with was, when I put that in, it said negative 0.5. And then what I'm going to do now is use the answer button, and then the calculator can keep reusing your same answer. So I'm going to go answer minus y1 of answer, y2 of answer, and I end up with, let's see here. So now I end up with negative 0.566311. But now that this has been stored in the TI-83, and the answer is being used, if I hit enter another time, it's going to recalculate everything with the new answer. So if I hit answer, now I get negative 0.567143,165. I hit answer again, I get negative 0.5671432904. You can keep going as many times, but now this is repeating over and over and over again. So you can just keep hitting enter, and your calculator keeps going through Newton's method. Okay, so let's try another one then. So if we wanted to find the intersection of two graphs, how could we do that with Newton's method? Well, what I want to do is I want to look at where root x equals cos x. And to do that, we could use Newton's method if we're looking for this. Okay. So that's what we do to find the intersection, is we make it equal to 0. And then what I'm going to do is I need its derivative. So the derivative of this function is going to be 1 over 2 root x, plus the sine of x. Okay, so here's my function. Here's the derivative. So when you do your work tonight, that's what I expect to see, that you show me you've got the function and the derivative. Then all I expect you to show me is the approximations you're getting. Okay, so let's put these in now. It's y equals square root x minus cos x. And the derivative is 2 root x plus sine x. Okay, so I've entered them in like we did before with the function and its derivative. So now all I'm going to get you to do to show me the rest of your work is go like this and tell me what's your initial guess here. So you may want to use your graph to see the initial guess. I would guess that somewhere around, I don't know, let's say you're, I don't know, let's go x0. Let's say the first one I'll pick is about, I don't know, 0.2. Okay, and, sorry? So now I'm going to use those y variables. So I'm going to enter them in. So it's going to be 0.2. This is my y1, and this is my y2. So it'll be 0.2 minus y1 of 0.2 over y2 of 0.2, and that will end up getting a solution. It's like a race. Let's see who can Newton it first. Oh, okay, so my guess wasn't that great. The next one I get is 0.604 something. Okay, so if I use 0.604, this time I get 0.641. And if I keep hitting enter, the next one I get is, I'm running out of room here, but 641,714 and 641,71437, and then that's it. It stops here at 641,7143709. Okay, so good luck getting that in any algebraic solution, but Newton's method can do it fairly quickly for us. So there's this some problems sometimes that you need to be aware of for Newton's method. So what do you think can go wrong with Newton's method? What are some things that Newton's method is going to have to rely on? Yes? Derivative can't be 0, or we divide by 0. Tell me more about the derivative. What else do you think has to be about the derivative? Yeah.
Higher than 0.
Right? That's so it can't equal 0. It can be negative though. Well, it assumes the derivative exists. So if the derivative doesn't exist, there could be a problem, right? So let's take a look at what happens if we try this one here, the cube root. So it's easier to see it with a picture. So let's put in x to the 1/3. So this is the cube root. Why is that not coming through there? Okay, well maybe I'll have to use this one to show it. I don't know why that's not... See, there should be a graph on both sides. I don't know why that other graph only shows up on one side. Just see if I've got it right. Yeah, it looks like it. because apparently in this calculator you have to call it cube root. So here's what happens. Okay, somebody give me any number you want. 5. Well, let's pick 2 because 5's not on the screen.
0.
Okay. So watch what happens with Newton's method here. It jumps over, finds another one. Is it getting better or
It's
getting worse? There's problems happening, right? So what do you think might be causing the problem? Why do you think it can't find it? There's no derivative at 0. That's right. So if you remember, for the cube root, that means my derivative, f prime of x, is going to be, so that's 1/3 x to the negative 2/3. So that's the same thing as there's going to be an x on the bottom. So when x equals 0, that's not defined. And it's a vertical. Remember we talked about that when we looked at the graph. We said as it goes up through here, the tangent line, well, it's not a very good drawing of it. But as we go up through there, let me do a better job of the cube root. So it's more like that. And as I go up through here, there's this vertical tangent line where it's not defined. So Newton's method can fail in those instances where it's not differentiable. Okay. Now, another thing that can go wrong with Newton's method, I'll show you a couple of pictures to help you see it. For example, in this one is not very useful for us because when I take my initial guess, it says, okay, find the tangent line. There's my second guess. Find the tangent line. There's my third guess. Find the tangent line. There's my fourth guess. And I just keep cycling. So it doesn't find the solution because it's a tricky set of tangents. Okay? And of course, the other thing about Newton's method we've already talked about is you might be looking for this point here, but it might actually find that one there. So sometimes that may make a difference, sometimes it may not. But one thing that's kind of neat to see is some of you may have done fractals with me before, but one way that the fractals are generated, this is actually the set of equations. This is the equation here. And what this is these map out the solutions. So for example, let's just say there were, let's say we took a graph. We'll take a nice simple one. Let's take y equals x squared. Oops, sorry, that's at x equals, right? So let's just take a nice simple one. Let's go -4. Okay, so you can see the two roots that are there. Sometimes I may put in an initial guess, and it may get this +2. I may put in an initial guess, and I may get this -2. So what I'm going to do to make my fractal is I'll say if the initial guess says +2, put a red dot on the screen where my initial guess came from. If it goes to the -2, put a blue dot. And then I'm going to have a screen with all red and blue dots depending on where it went. And I might even say, like, if it doesn't produce an answer, notice right down here at 0, it wouldn't produce an answer because it's going to be a flat tangent, divide by 0. Color it black because it doesn't give an answer. So then all those colors mix and match together, and this is what they look like when you use Newton's method and say, there's 6 colors in here because there's 6 solutions to this equation. Some go to a particular answer, they've been colored green. Others go to another one that's colored blue. Others go to another colored orange. So it's kind of like a graphic display of all the possible solutions using Newton's method. So, I don't know, it looks pretty too, right? Okay. So anyways, for homework, again, when you do this, I expect you to use your calculator, but I still expect you to show me the function and the derivative as you do it.